I know this picture is how most of you are starting to feel. I know this is not an easy course, trust me, I know that. You need to spend a little bit of time each day, and that's what will help you get through this. Also, watching these lecture videos like you're sitting in the lecture classroom taking notes instead of jumping straight to the homework problems. I see many of you jumping straight to the homework problems and not watching my lecture videos, because I can see how many students have watched my videos and I'm looking at 6, 8, 4, 2, and if I have like 20 something students, that tells me you're not watching the lecture videos. So I don't even know how you can hear this if you're not watching the lecture video, but I'll send out a mean email here in a second. All right, so let's look at the graph of a function versus what a sign chart is. So a sign chart tells you the sign of the derivative. Remember, the derivative is the slope. So if the slope is positive, we'd have a little plus sign there. If it's negative, a little minus sign there. And where the slope is 0, okay, where it goes horizontal, then that's where you see the little 0. So I can see in this case that this function is increasing. It hits 0, decreases, hits 0, and increases by the derivative. And so if I took the derivative, 3x squared minus 3, because you have that shortcut down, really good, right? I factored out a 3. I notice x squared's the difference between squares, so I factored it into x minus 1 and x plus 1. And that's how I get these zeros here. Okay, in other words, if I wasn't looking at the graph, I get these values, 1 and negative 1, because that's where the derivative equals 0. So if I have a function that's increasing and decreasing, if the derivative's positive, derivative's the slope, that means it's increasing, negative, decreasing, and 0, constant. So I want to find the intervals on which a function is increasing or decreasing, given this function. Well, if I want to know if it's increasing or decreasing, that's slope, derivative, so I find the derivative. 8x, 8, x squared, bring the 2 down, subtract 1. I set my derivative equal to 0, and then I solve for x. So I go through and I have this set this equal to 0. I'm going to solve for x. I move the negative 8 to the one side, and I divide both sides by negative 2, and I get x equals 4, which is where the function has a horizontal tangent. So I found where the derivative equals 0. Okay, that was from here, x equals 4. So now I can create what's called a sign chart, which says at 4, that's where the derivative equals 0. I just pick test numbers, meaning I pick something to the left of 4, and I pick something to the right of 4. I plug in 3, that's to the left of 4, and I get 8 minus 2 times 3, which is 8 minus 6, gives me 2, which is a positive. Then I plug in something greater than 4, like 5, so I get 8 minus 2 times 5, 8 minus 10, I get negative 2, a negative value, so that tells me it's decreasing. So I can just plot values here, and I can actually see at 4, I have a horizontal tangent. To the left of 4, it's increasing. To the right of 4, it's decreasing. This 4 value is also called a critical value, critical number, critical point. Okay, you may hear it called many different things. I typically call it a critical point. Sometimes I'll say critical number because that's what your book uses a little bit more. And so where you have a critical point is where the first derivative equals 0. So if I said find the critical points, you would find the derivative, set it equal to 0, and solve for your variable. A critical point is where the first derivative equals 0. So in these cases, it's where you have horizontal tangents, because if the derivative equals 0, the derivative is a slope, and if the slope is 0, you have a horizontal line. So for any function f a point P in the domain of that function where the first derivative equals 0, or we're going to see something else can happen, the derivative is undefined, is called a critical point. So it's not always just where the first derivative equals 0, it also is where the first derivative is undefined. So if I had this example, find critical values and where the function is increasing and or decreasing. Well, how do I find the critical? I need to find the first derivative. This to me looks like a chain rule, so I'm going to set my y equals u to the 1/3 power. My u is 1 minus x. I take my derivative of my y, which I bring the 1/3 down. I subtract 1/3 minus 1 to get negative 2/3. I take my derivative of u. I get negative 1 because the 1's a constant, goes away. So my chain rule says to multiply those two pieces. I substitute back in my u. And then I just simply picked this 2/3 up, this negative 2/3, moved it to the bottom, which made it a cubed root, and this squared. You didn't have to do this step, but the reason I do this step is it makes it very, very clear to see if I plug in a 1 right there, bad things are going to happen. Because if I plug in a 1, I'm going to end up dividing by 0. So 1 is still a critical point. And notice that I can plug in 1 into my original function because I get 1 minus 1, which is 0, to the 1/3 power, which is still 0. So it is continuous. It's just the derivative does not exist at x equals 1. So it's a critical point, but something apparently is going on weird there. So let's see. What I do is I say it's not defined. I pick a value to the left of 1. I pick 0. Pick a value to the right of 1, and I actually see both of these, and where am I plugging these in? I'm plugging them into my derivative. Okay, so when I plug in 0 into my derivative, so that's what I'm looking at, I see I get a negative value, and I plug in 2 and I get a negative value. And so what happens, and you can see why, this little negative sign right there, don't lose that. And so what's happening is this function is decreasing, then something weird is happening, and then it's decreasing again. Well, what's happening, you actually have what's called a vertical tangent. So notice this vertical slope. If you remember when you were in algebra and you talked about slopes, and if you had a vertical line, you said the slope does not exist. Well, isn't the derivative the slope? So it's not defined there. Let's do the same thing. Find the critical values and where the function's increasing, decreasing for this function. I don't feel like doing the quotient rule, so I'm going to bring the x minus 2 up to the top and put it to the negative 1 power. So that way I can just simply use my chain rule. U to the negative 1. My u is what's inside. I take my derivative of y. I take my derivative of u. I multiply those two together because you've been practicing the chain rule, right? This is all chain rule stuff. And then I substitute back in my u. And again, I like to bring my negative exponents to the bottom because that helps me see when the function would not be defined. So I can see already if I plug in 2, the derivative's not defined, but also notice it's not even defined for the function. So this is a key here, is that the function, it's not defined, the derivative, it's not defined, but we're still going to use that to partition our sign chart. Even though it's not a critical point, we're going to use it as a partition to be able to pick values to the left and values to the right. See that the derivative is negative for both. If I graph this, what's actually happening here is why my function is not even defined, is I have a vertical asymptote. And so I can see my function is decreasing from negative infinity to 2 and from 2 to infinity, but at 2, the value of the function doesn't exist. There's an asymptote. and certainly my derivative does not exist. So the critical numbers of a function belong to the domain of the function, and they also can just be partition numbers. Your derivative may have a partition number that does not belong to the domain of the function, like what we just said. So they're not critical numbers. They're just a partition number to partition off our sine graph. If f is a polynomial, because we know polynomials are continuous, then both the partition numbers for the derivative and the critical numbers of our function are solutions to our derivative equals 0. Do not assume that all partition numbers for the derivative are critical numbers of the function, because to be a critical number, f prime, the derivative, must also be in the domain. And that's the example we just had. The intervals on which a function is increasing or decreasing must always be expressed in terms of open intervals that are subsets of the domain of the function. So in other words, when we say where is a function increasing and decreasing, we are looking at the actual function, not the derivative, and then we put it on open intervals, meaning like from -infinity to 2 and so on, like what we just did. Now, if you think about it, what's nice about critical numbers is it allows you to find max and minimums. And we'll talk about more about this later, but if I'm looking at a sign chart and I have a critical number, and let's just kind of draw this out a little bit, and my function is decreasing, it goes to 0 and increases, I can see that that's a local minimum. If it's positive and it's increasing and then it goes 0 and it decreases, I can see that that's a maximum. So this is kind of nice because I might want to know where is max profit. Well, what I'm going to do is I'm going to set my derivative equal to 0 and find this critical number here, and that would give me my minimum and my maximum. If you have something going on here with positive goes flat positive, or negative goes flat negative, then as you can see, this certainly is not our local extremum, meaning no local max or min. So if my derivative is 0, I have a horizontal tangent. So these are the 4 ways you can have these horizontal tangents: at a minimum, at a maximum. Just our function just went constant for a little bit and then it shot back up, went constant, went back down. Where we have these vertical tangents, as you can see all here, our derivative is not defined. But our function's defined, it's just our derivative's undefined. All right, at the beginning of this lecture, I said if I asked you to find a critical point, how would you find it? You would find it by finding the derivative, 3x squared, 18x, 48, set the derivative equal to 0, solve for x. Now what I notice is all of these I could factor out of 3, and then I just have to factor this inside the parentheses. So that algebra is coming back to haunt you, right? You're going to have to remember how to factor. Then I set both factors equal to 0, because what would make this equal to 0? One of the factors equals 0. I don't care about that 3 because it doesn't have a variable on it. And so I said x minus 8 equals 0, or x plus 2 equals 0. So x equals 8 and x equals -2. This is a polynomial, so I know it's continuous. These would be my critical points. So I make my sign chart. I plug my critical points, put them on my sign chart, and then I pick values within these 3 intervals and I plug them into my derivative. Because my derivative, remember, if it's positive, tells me if it's increasing. If it's negative, it's decreasing. So I don't know, I picked -3. I plugged in -3 into my derivative and I get a positive number. I don't really care what that number is. I mean, it could be important later because it tells me how fast it's increasing. But all I care right now is in this interval, this function's increasing. I pick a value in between here. Always pick 0 when you can, because that's lovely, right? It makes everything go away with variables. I see I get a negative. I plug in something bigger than 8 into my derivative, like 9, and I see I get a positive. So what this tells me is pretty much what this function looks like. It's increasing, it goes flat, decreases, goes flat, increases. Well, where it goes flat, I have a maximum. Where it goes flat here at 8, I have a minimum. And so I could go back and just graph my original function, and I can see that matches my original function, okay, where I have my max and my min. Now these numbers, my y values, remember you have to go back to your original function to get those. So I can see I have a critical point at -2, 104, and a critical point at 8, -396. The first critical point's a local max. The second critical point is a local min. And I can see where the function is increasing. So it's increasing from -infinity till it gets to -2. It's also increasing over here from 8 to infinity. And then decreasing between my local max and local min from -2 to 8. What's kind of nice if you remember this in algebra, if you don't, it's not a big deal, but this theorem says that if I have a polynomial of a degree is the highest exponent, so this degree is 3, then the function at most, okay, at most has n x-intercepts. So at most, this is going to have 3, 1, 2, 3, x-intercepts, and at most 3 minus 1, 2 local extrema. 1, 2. That's my max and min. Again, it's not a huge deal if you don't remember this, but it's kind of nice because it helps you say, oh, well, that would make sense based off of this degree. All right, so let's look at the graph of the derivative. Notice this is b prime of t. This can get a little crazy for students because when you look at this, you think something's decreasing, but it's not. How you read the graph of a derivative, if you're above the x-axis, or in this case it's a t, then the derivative is positive. If you're on the x-axis, your derivative is 0. If you're below it, your derivative is negative. So basically this is saying my derivative is positive, but it's starting to decrease. It hits 0, it goes negative, hits 0, and then starts to increase. So let's look at the actual graph and see if that makes sense. Let me get my little pointer thing back. So over here I said the derivative is positive because it's above the x-axis. Well, look at the function. It's positive, it's increasing. Then it hits 0. Right there, hits 0. Then the derivative decreases, so goes negative. My function decreases at 10, 11, 12, right here, 10, 11, 12, it goes to 0. And then it goes back increasing. What I like to do with these is I like to put them on top of each other because it helps me line up my horizontal tangents with zeros here. And so I can see my original graph and then my actual derivative by actually lining these up. If I have an actual function and I want to produce the derivative, well, by looking at this, I can see that, let's just, before I show you the picture, I can see that my derivative, because it's my slope, is positive, and then it hits 0 at 500. So it's positive, and then it hits 0, and then it goes negative. So as you're going to see, that's all the graph looks like. Is it's positive above the x-axis, 0 on the x-axis, negative below the x-axis. So once again, lining these up to me helps to be able to go from the actual graph of the function to the graph of the derivative. Because remember, the graph of the derivative, you're graphing the slopes. That's what this is. If I found the slope at every single point on this line, that's what I'm plotting down here, is just a number for the slope. So when the slope at 500, the slope is 0, I plot a 0.